We now turn to the operations and data types that are supported in GSL, SL. As we'll see, they'll be very much like what we're familiar with from C, C++, but we add a few things to that. We start with the basic C types: int, float, bool. No, don't believe there's doubles right now. There's some reserved words that allow for future expansion. Also, it's pretty tight about ints and floats. You have to do casting if you're going to switch between those types. It adds the types we've seen, like matrices and vectors of 2, 3, and 4 dimensions, which are what we need to do computer graphics. So there's a vec2, a mat2, mat3. They're all composed of floats. If you need vectors or matrices of integers, then there's IVec and IMAT and BVec. If you need an array of Booleans, you can do that. They're stored by columns. This will be an issue we discuss in the text, and you may get is that the OpenGL standard for how storing by columns sometimes comes in contradiction with what you're used to in languages like C, and you'll have to do some switching. We take care of that in the flatten function for the most part, so you'll usually be able to do what you're familiar with, and the switch to columns will be done within that function so that GLSL gets what it expects. You can do standard referencing by just using two indices as you would in C and C++. You also have standard C++ style constructors that you can use for the types. So if we want to create a vec3, we can just say vec3a is vec3 and give it the values. We can also create a new vector by copying an old one, as in vec2b is vec2 of a. So those simple C++ style operations are there, as are overloading of those basic vector and matrix types. There are no pointers in GLSL. It does support C-like structures. They only come in occasionally. You not only, as we've seen, that both the vertex shader and the fragment shader are complete programs that have a main in them, and they can also refer to other functions that you can create within the same file, and so you can use C structs to go back and forth from functions. But for what we'll be doing, that probably is not going to come up at all. Because the matrices and vectors are in fact basic types, what you want to do is be able to pass them around, and they're very, very simple because they pass around just like integers or floats. So that's simple. Variables are passed around because there are no pointers. They're passed around by copying out to the function, and if you return something, it's returned by copying back. Now, one thing that it introduces is a number of qualifiers, more than you're familiar with probably from other languages, like the const qualifier you use in C and C++. The reason for having more is that when things change can occur from the application programmer's point of view at many different ways. So sometimes you want to have, if you're changing, say, a color, you want that color to apply to the entire primitive. Other times you want to have a separate color for each vertex, and many times you want to have a different color for each fragment. So the question is, how do we do that when functions can occur anytime within an application? And the way we do that is to have a variety of qualifiers that say when things are allowed to change. Now remember, as part of this, that keep in mind that attributes that we send to the vertex shader, or things that are created in the vertex shader and sent on to the rasterizer, are automatically interpolated across the primitive to get values of that attribute for all the fragments that are being generated by by the rasterizer. So we're going to see examples of this, but typically if you have, say, red assigned to one vertex of a line segment and you assign blue to the other end of that line segment, and those two vertices go to the rasterizer, what's going to happen is that the fragment colors all along that line segment that are generated by the rasterizer are going to interpolate between red and blue, and so in the middle you'll see magenta and various shades that get you from blue to red or from red to blue. So we'll see that coming up in a minute or two. So the first one is the attribute qualifier, which refers to things that change only on a vertex by vertex basis. One of them is the built-in GL position, but there used to be many, as we've said before, that have been deprecated, so what we have to do now is define them within our program. So typical ones are things like color and texture coordinates, but we also can have many that are particular to our application. So if you're working with, say, a model of some structure and you want to assign a temperature, say it's modeling a piece of metal that's being heated up and you want to assign a temperature to every vertex, that becomes an attribute. So one of the nice things about deprecating some things that were built in, like colors, is it gives you a lot more freedom to say, these are the attributes I need for my application. So I'm going to send over for each vertex a temperature. So I identify that in the vertex shader as an attribute variable that comes over from the application, and we'll use, say, a float, and its value will be called temperature. So now I can refer to temperature in the code for that shader. You can have multi-dimensional attributes. So for example, if you're doing some sort of fluid flow problem and you have at each point or at each vertex there's going to be a velocity, a magnitude and a direction of the flow, that might be an attribute that's set inside of the application, and now it's a vec3 because it has an x, y, z component, and we send it off to the shader as an attribute, or it's referred to as an attribute qualified variable. Now, just a note, and you'll see this again in a while, is although GLSL shaders work across all versions of OpenGL, the shader language has evolved, and the version that is tied to WebGL is one of the first versions of the shader language that uses the attribute qualifying. That's been replaced, for reasons we'll see a little more clearly in a few minutes, by in and out, because in and out are much clearer. So instead of saying in float temperature, instead of saying attribute flow temperature, we would say in flow temperature, which would say that's coming in from whatever set off the application that set off that vertex shader. And likewise, if we were sending something off to the fragment shader from the vertex shader, that would be an out qualified variable, which makes things, I think, a lot more clear. But in GLSL right now, with their attribute qualified and the other qualifiers we'll see in a few minutes. Now, the attribute qualified variables, we said, can change on a vertex-vertex basis because they're in the shader. It says attribute qualified, and that kind of says, oh, that's for this particular invocation of the vertex shader. Now, what about things that are the same for the entire primitive? What if we want to assign a color that's not going to be changed for the entire triangle, say, or a temperature that's not changed? Well, those are called uniform qualified variables. They're set inside of the application program and sent over to the shader, where they can't be changed within the shader. So you cannot make changes to them which are on a vertex by vertex basis, because you want them to be the same for the vertex. So we pass information. A typical one would be if we have some animation and what we're doing depends on the time, then we can send the time over as a uniform qualified variable, and that time will be the same for all the vertices that come from that primitive. Another one we'll be seeing very quickly is when we start talking about rotating things in real time. We have a rotating cube and a rotating square we'll be talking about very soon. The amount of rotation, an angle theta, is going to be the same for all of the primitives that are all the vertices that are on that primitive, and so we want to send that over just once as a uniform qualified variable. The third kind is called a varying qualified, and it seems a little weird to call something a varying variable. That's been deprecated by in and out, but the idea is this, that you set something within a vertex shader, it then goes to the rasterizer and it's interpolated. So that variable actually varies over the face of that primitive and is then given a different value to each invocation of the fragment shader, because each fragment that is generated by the rasterizer will have a different interpolated value of that primitive. And it's called varying both in the fragment shader and in the vertex shader. And in fact, that namespace is shared. So if you call something varying, say varying vec4 color in the vertex shader, and you use that color in the fragment shader, it has to be called varying vec4 color in the fragment shader. Recently, this in-out that I just talked about really applies to this, where in the vertex shader, you would call it an out because you generate the color there and send it out to the rasterizer in the fragment shader. From the fragment shader's perspective, it's an input variable, so it would now be replaced by in if you're doing a more recent GLSL, say, in desktop OpenGL. Now, because if we go think of things like color, we have color potentially in the application. We have color in the vertex shader. We have color in the fragment shader. We really need some sort of a naming convention so we don't confuse all these things. So we've adopted the following one, and having thought about this for a long time and tried various things, there's no system that's perfect. But let me give you the system that we've decided to use in the book, and try it. If you don't like it, you can certainly use your own naming convention. So what we decided to do was say that attributes that are passed to the vertex shader, they come from the application, are going to be given names that begin with a V. So you've seen some. We've talked about V position, and we'll talk about V color, and that'll mean something that's an attribute variable. So it did come from the application, but it's being used in the vertex shader. Likewise, varying variables are going to be specified within the vertex shader, but used within the fragment shader. So we're going to begin their names with an F. This will be called F color. Now remember, because the vertex shader and the fragment shader for variables share the same namespace, they'll be called F color, for example, in both shaders, but at least you will know in the vertex shader, that's something that's going out to the fragment shaders. Now we decided to not put anything in front of uniform variables. And so the potential confusion is, I think the good part of this is it tells you where things are actually being used, but you have the same name in two different places. So for example, with attributes, we'll use V position in the application and use V position in the vertex shader, even though they're different entities inside. But that will lock it in. They're coupled, but they're stored separately, because one's in the application, the other's in the shader. Likewise with varying variables. Now uniform variables, we made them unadorned. One reason is that a uniform variable comes from the application, but it can go to either shader. And so we just said, okay, let's just not put a letter in front. One of the other books, I think, would use an A to say it came from the application in front, and that's probably okay too. So let's look at using those. So here's, again, a very simple vertex shader, but in this case, it has two of them. The attribute is V color because it's coming from the application, but it's going and being sent off to the fragment shader through the rasterizer as a varying variable, so we're going to call it F color. And just as the position is just copied over because we assume the coordinates have been set right, copies over a position by just setting the GL position to V position, the fragment color is being set equal to the attribute V color. Now that is going to be interpolated. So when F color gets over to the fragment shader, the fragment shader is going to see the interpolated value. But I think this conveys what we're trying to do here, is that the color that's set in the vertex, there might be some more complicated code that's set in the vertex shader, is now being sent over to the fragment shader. Now the fragment shader now has, again, the medium precision. It's getting a color here. This should be F color here. It gets F color as a varying variable, and then it's setting the fragment color to the color that came out of the rasterizer. So with this, just change this little thing to F color up here. Okay. Now, how do you get that stuff there from the application? Because all this stuff is, at least in this simple example, is starting in the application. So there are two situations. We're either going to send an attribute over, or we're going to send a uniform variable over, and they're roughly the similar kind of thing. And here's where, again, the name convention comes in. If we're sending over an attribute, the attribute is going to be different for every vertex. So we need to put that information inside of a buffer. So here's what we've seen before. We set up a buffer. If it's for colors, I'm calling it the C buffer as opposed to V buffer, which I've used for vertex attributes. So I set up that buffer. I bind the buffer to make it the present buffer. And now I send over the buffer from some array colors that I created inside of my application code. We use, again, the flatten function to convert the JavaScript array into just a string of floating point numbers that the GPU will understand. Here's the part that ties things together. Say, well, how do I tie those variables in the application to variable names in the shader? Well, that's through getAttributeLocation. So again, we talked about this a little before, but let's look at it with our naming convention. So I have something in that vertex shader we call vColor, and it's in our program object. I'll talk a little more about program objects in the next lecture or two. But within that program object are our shaders, and the vertex shader has something called vColor. Now I've decided in our convention I'm going to call the value in the application also vColor. But remember, they're different things. This is a variable inside of the vertex shader. Over here, what you're getting is a location in some linking table of where this variable is found, and I'm calling it vColor, so I know that these are referring to the same thing. And now I just give it its format and enable the vertex attribute array called vColor. Okay, so that's our standard convention. You'll see it's the same when we send positions over. This is just becomes V position, and this becomes V position and V position and V position over here. Now, uniform variables, a little more straightforward because they're not changing, and it's just usually just one value. It's not an array that we're sending over, so we don't have to worry about a buffer. So here's a simple example where, say, what I want to do now is make the entire primitive have this red color. So I define a color in my application, vec4 color, red, fully on, no green, no blue, and it's opaque. And now I have a variable inside of the vertex shader called color. And so what I'll probably do there is output that color to the fragment shader each time. But in the vertex shader, it's called color. Now I have to get its location again from the linkage tables after I've compiled and linked together all my shaders into my program object, and I'll call it color loc to distinguish it from the color here. But it's giving me where is that color in there, and now I can refer to it, and now I simply use GL uniform to send over at that location to send over this variable. There's a form of GL uniform for each type of thing I'm sending over. So this is say I'm sending over a 4-element array, and each element is a floating point. There's GL uniform 2s, 3s, and 4s. There's GL uniform matrix for sending matrices over. F is for floating point. I is for integers, and so on. Then in the fragment shader, if I want to send, I could do this either to the fragment or the vertex shader. I send it. That's going to receive this uniform value. I now have uniform saying I'm expecting this to come over from the application, and now, trivial example, I just set the fragment color equal to this color that I sent in. So now everything will have the same color because this uniform variable applies to the whole primitive. Okay, so now let's talk a little bit about some of the functions that are in there. The simple part is that all of the standard C, C++ like functions, Java functions are in there. So all the trigonometric functions are in there. All the standard arithmetic functions are in there. You get a few more to help you with the kind of geometric and vector calculations you might want to do. So there's a length function in there that'll give you the length of a vector. There's a reflect function that'll take two vectors and give you one will be the normal to a surface, the other will be an incoming vector, and it'll give you the reflection direction. We'll talk about that later when we talk about lighting. If you want to normalize things, to have unit length, normalization functions are in there. So there's a whole bunch of helpful functions that are in there. And as we've said before, the primitive types, including matrices and vectors, have overloaded arithmetic operators. The one place it gets a little tricky, see, for things like vectors, it's pretty straightforward. If you have vectors A and B and they have the same dimensions, then you can have a vector C, which is A plus B. That's very simple. The place it gets slightly tricky is when you start doing matrix multiplications, because remember, if you multiply two matrices together, the number of rows in the first has to equal the number of columns. The number of columns in the first has to equal the number of rows in the second, so that the operation of B times A, where one of them is a matrix and one of them is where, let's say, B is a vector and A is a matrix, may exist while the operation AB might not exist depending on the dimensions. However, if B is a vec4 and A is a 4x4 square matrix, then if in matrix algebra, if you take B times A, it's a 1x4 times a 4x4, which gives you a 1x4. And likewise, if you take A times B, if you take A times B, A is a 4x4 times a 4x1, which gives you again a 4x1. But one's a column vector, one's a row vector, and the numbers in general will come out to be different, even though both exist. Both of them internally are stored just as one-dimensional arrays with 4 elements. So even though it's really nice that this is supported and doesn't require you to always have things that are row matrices or column matrices or row vectors or column vectors, as long as the dimensions make sense, this overloaded operator will work, but you have to be a little careful to make sure that you want BA and not AB, because in terms of what's inside, all of the vectors, whether they signify row or column arrays, are stored as just 1D arrays. Okay, now, last one that's kind of neat, is because GLSL is really aimed at doing graphics, and the kind of things that arise in graphics have sort of conventional names, like we talk about RGB colors, we talk about X, Y, and Z for positions, but all of them are internally stored inside of arrays, 2, 3, and 4-dimensional vectors. So what OpenGL does is give you 4 different ways of referring to individual elements or doing selection. So you can do it the standard way and say, okay, I have A is a is a vec4, I can refer to a of 0, a of 1, a of 2 by using the standard bracket notation. But I also can say, well, it makes, the point of this is it's going to make your code a lot clearer, is that if it's a position, then a of 0 could also be referred to as a dot x using the dot selection operator, and a dot y is a of 1, and so on. But that wouldn't seem very clear if the vector was a color. So I can also refer to a dot r if that's storing a color, a dot g, a dot b. A dot a would be the opacity component, and it would be exactly the same. So I could use a dot x for that and a dot r, but when I write my code, I want to make it as clear as possible. So when I use colors, I'll use the RGBA. When I'm talking about positions, I'll use x, y, z, and we get to homogeneous coordinates, we'll use w for the fourth component. Later, when we talk about texture coordinates, the convention for texture coordinates is to use STPQ. Notice that none of these letters are repeated, so a dot s would be the first component of a texture coordinate vector, and that's very, very nice. The other little thing that's nice is what's called swizzling, which lets you choose groups of components and switch them around. So, for example, if I refer to YZ here, I'm referring X is the first one, Y is the second one, Z is the third. So a dot YZ would be a vec2 that was composed of 2.0 and 3.0, the second component and the third component. But I can also do swapping. If for some reason you want to swap the XY direction, you could set B, if B is a vec4, you can set B equaled a dot yxzw. That would leave the z and w with the third and fourth components alone, but swap the y, the first two, the x and the y. So this can be very, very handy. It can be very handy. Often you want to just grab the first three out of a four-dimensional one for passing around or for some color. This makes it very, very easy to do. And later you'll see the standard operators, principally the trigonometric operators, which will give you the choice of doing a certain operation within the shader or doing it within the application. Hopefully your first assignment will give you a chance to explore that.